Well, congratulations. You found the hidden link. And in this link, I'm going to show you how to solve number 1. So, we know that according to this Arrhenius equation, that the equation for the Arrhenius equation is the form of a straight line. It means it's got y equals mx plus b. That means this is y, this is x, and this guy is our slope, where r is a constant, 8.314 joules over Kelvin moles. So if we know the change in the natural log of K, and if we know the change in the inverse of temperature, we can find the slope and solve for activation energy. So I'm going to let my calculator do all the heavy lifting on this guy. So here's what we're going to do. We're going to tell the calculator to do a couple things. Now watch this, because this thing is pretty powerful. And it's kind of neat what it can do. So let's clear all of our memory first. All right. So let's go to some statistics, and we're going to enter some things. Let's go to L1. We're just going to enter these in order. It doesn't matter where we put them, because we can instruct the calculator to do what we want later on. So we're going to say 4.9 times 10 to the negative third, and the calculator, is going to convert this into a long form. So that's going to save us some time later, 0.0049. So when we enter the next one, it's one more decimal place, so 0.0005. There's our 5 times 10 to the 4, and the last one is 0.000035. So I don't have to mess around with this scientific notation, so the calculator is going to do it for me. For temperature, we're going to go into L2, and we're going to enter these. Now watch what happens, because the first thing the calculator wants, the equation wants, is temperature in kelvins. So I'm going to instruct L3. Notice that I've got L3 highlighted. I'm going to instruct L3 to take everything it's in L2, which is our temperature in Celsius, and add 273. Then, because the column after that is asking us to invert the temperature, I'm going to instruct the calculator to take everything that's in L3 and invert it. We'll do that in L4. So L4 is you're going to tell the calculator to take everything that's in L3 and invert it. And lastly, I'm going to scoot this over here, because the last column we want is the natural log of Kelvin of the rate constant K, which we put in L1. I'm going to tell the calculator to take L5. Remember that L1 is where we put all of our rate constant K. So I'm going to tell the calculator that in L5, I want to take the natural log of everything that's in L1. Okay? So that means that now we have inverse of temperature in L4, and the natural log of the rate constant in L5. Now, you can fill out these data if you want, and I'm not saying that it's a bad idea to do that. But in the interest of time, I'm going to pause and then fill in the data so you can see what that looks like. Ta-da! So there is the data. Now remember that we want the slope. That's this guy. Negative EA over R equals the slope, which is going to be the rise over the run. Well, the rise is the y-axis. That's ln of the rate constant K. So that's going to be the difference in the natural log of K. And the run is the x. So that's the difference in the inverse of temperature. Now, this would be where I would tell my students to find the delta 1 over t and find the delta natural log of k, but that's not necessary. All we want is the slope. It even says to make the appropriate graph, but we don't have to because we have this guy. So what we are going to do, we're not even going to make the graph. I mean, you can if you want. You could go here, and I already have this set up to graph L4 versus L5, L4 being inverse of temperature in kelvins versus L5, which is the natural log of the rate constant K. But that's not necessary either, because all we want is the slope. So what we're going to do is we're going to instruct our calculator to take the linear regression of L4 on the x and L5 on the y. When we calculate this, this gives us the slope, negative 12,447. Now, if I was really going to be a stickler, I would be paying attention to units, but let's not worry about that. 12,447. Something like, well, actually, interestingly enough, the only units are inverse of temperature, which is in the denominator. So there really is a unit, and that's kelvins. Okay? Now, we want to find the activation energy. We know that activation energy over R, which is the slope, what we just found, 12,447 kelvins. Well, you just found the slope. So if you know that this has got to be equal to negative activation energy over R, where R is a constant, 8.314 joules over Kelvin moles, and look what happens to kelvins. It cancels. So do our negative signs cancel, because activation energy is obviously going to be a positive number. So let's take this answer, negative 12,447, and multiply it by the value for R, 8.314. We've already shown how the units cancel, and our answer should be in joules per mole. And of course, negative slope is equal to negative EA over R. So this is a positive number, 103,484 joules per mole. Aren't you glad you found this link? Now let's go down and take a look at number 2. This equation that we're looking for is the Arrhenius equation, but it's set up with only 2 values for rate constant K, EA over R, multiplied by the differences between the inverses of temperature 1 and temperature 2. Okay, and in this question, it's asking us for the rate constant at 372. So what I'm going to do is I'm going to assign everything with a 2 is what we're looking for. All right, and that means that we have a rate constant K that we're looking for, and we have a T2 that we already know, which is 372 degrees Celsius. Okay, so I'm solving for K2. So here's what this looks like when I plug everything in. Natural log of K2, which is what we're looking for, over K1. Well, there is the rate constant at our first temperature, 282. So I'm going to say 352 times 10 to the minus 7th seconds to the negative 1 is equal to EA. It tells us right here the activation energy is 186,000 kilojoules per mole. And because R is in joules over Kelvin moles, let's get those units to be equivalent. 186,000 joules over 8.314 joules over Kelvin mole. And finally, the inverse of temperature 1, which is 282 degrees Celsius, we want that in kelvins. So 282 plus 273, 555 kelvins minus our temperature T2, 372. So let's get that into kelvins as well. 372 plus, some of you guys can do this in your head. I can't. 273, 645. Okay, we're solving for K2. So watch what happens. I'm going to take care of everything on this side. And I'm going to do this. I'm going to say 186,000 divided by 8.314. And then I'm going to multiply this. So I'm just going to press multiply. That's going to take my answer times the quantity of the inverse of 555 minus the inverse of 645. This is this whole side, 5.6246. So, if you're interested, there's only one unit. Actually, there aren't any because this is joules over moles. Sorry, so those cancel and that cancels. And we've got kelvins and kelvins and kelvins, and they all cancel, so we're not really even worried about our units. What we know is that the natural log of the quantity K2 divided by 3.52 times 10 to the minus 7th seconds to the negative 1 is equal to 5.6246. So, to get rid of this natural log, we're going to take the whatever you call that reverse function of natural log, and that's going to be this shift function here, e to the x. So we're going to say shift e to the x, and since this was the last answer we had, we'll just plug that right in, and this is what we get. So now what we have is that K2 over, let me do this over here where I have some more space. K2 over 3.52 times 10 to the minus 7th seconds to the negative 1 is equal to 277. 277.165. What is K2? Now, before we even hit a button on our calculator, we are increasing the temperature. Do we expect the rate constant to increase or decrease at a higher temperature? Your kinetic molecular theory should tell you that answer. So we're simply going to tell our calculator to take 277 and multiply that by 3.52 times 10 to the negative 7. Will our rate constant increase with an increase of temperature? 9.76 times 10 to the negative 5th. And we can assume that since the units didn't cancel, seconds to the negative 1. Aren't you glad you found this secret link? And that, ladies and gentlemen, is the last one.